Hello, today I'm going to be doing a tutorial on how to compare steady laminar flow over a 2D cylinder in FreeStream to flow over a sphere of the same diameter and Reynolds number. This will be a very similar tutorial with a lot of overlap from my previous tutorial for STAR-CCM. However, the repetition will be good for you, and for those of you who are just joining us, you'll be able to start from scratch. So the first thing you want to do, of course, is load STAR-CCM. You can type into your browser, launch it however you want. So once it loads, alright, it's loaded. Now we can get started. It's important to note that if you don't have these properties, windows and output windows, and you want them, you can just click on window and the properties or output to select the output windows. And if you click on them, they'll appear. So the first thing we're going to do is, of course, start a new simulation. If you wanted to load a simulation, you'd obviously choose this one. It's really similar to the new simulation, only you would specify what file you're planning on load. I'm not going to go through this step, mainly because I don't want to show you my license file because it is unique, and I don't want you guys to use my power on demand licenses. However, so you would follow the instructions given by your instructor. Alright, so now that it loads, one important thing to note, check first of all, is there's a server idle time limit is 0.1 hours. Instructions on how to set this should be in your instructions provided by your instructor. However, it is really important that you have this done because many of these things, for instance, the class license I'm using works on power on demand licensing with hours, and even if this is running in the background and not doing any calculations, it's still charging hours. So if after 0.1 hours, it will save it to a different file. It will just save it to an idle file name and log out. That way you're not wasting all your hours. So make sure you have a server idle time limit set to a reasonable amount. So the first thing we're going to do is create our geometry. So by expanding this tree, you can see that the options here are 3D CAD models. It's important to note that STAR-CCM only works in 3D initially. It's a 3D mesher, but you can convert from 3D to 2D. So, but in order to create your geometry, you have to create a 3D CAD model, and then you can input them as a single. You can convert that 3D CAD model to a 2D surface. So if you right click on it and click new, once we're at this screen, we're going to start to create a sketch in the XY plane. The reason we choose the XY plane is that when we convert from 3D to 2D, essentially anything that's in the Z plane, Z equals 0 plane, will be used. So if we drew something in the YZ plane, only the things that barely touch the Z equals 0 plane is what would appear in the 2D sketch. So we want to sketch on the XY plane, that way the full sketch is visible when we do that conversion. So we right click on it and create sketch. Alright, now that this screen has appeared, if you zoom in, you can see that there's a bunch of grid lines. You can set the spacings of that grid lines by clicking down here to set sketch grid spacings. Sketch grid spacings. So we're going to keep this as it is. Additionally, you can toggle on and off the snap to grid function. This is enabling it to, when you're selecting a point, whether or not it's just you can place it anywhere or whether or not it snaps to the grid. So we're going to keep snap to grid on. The first thing we're going to do is create a center point circular arc. It should be noted that we're only going to create half of the flow domain, and across the line, the bottom line here, we're going to call it a symmetry plane or an axis, depending on whether we're doing a cylinder or a sphere. And there are different ways to make this sketch. I'm going to do it what I consider the easiest way. However, you can do it however way you want, as long as you end up with the same sketch. The first thing you do is create a center point arc, which is going to be the cylinder that we use. So we select that tool and click the center at 0, 0. And we're going to just place this, click somewhere over here, and then click somewhere over here. making sure that they're 180 degrees across. So if you click on this point right here, you can see that the point is 0, 0. We want it to stay 0, 0 because as of right now, you can actually click and drag that around. So if you right click on that, you can apply a fixation constraint, and that's preventing that from moving. Additionally, I want a diameter of 0.1 meters. So if I right click on this, I can apply a radius dimension of 0.05 meters, which essentially is a diameter of 0.1 meters. So that's exactly what we want. So now what we can do is we can apply a rectangle around this. So the easiest way is to use this 2 rectangle points where you press 1 here, click, and then click on the opposite corner. And we want the distance from this point to this point to be pretty far away. Again, I'm going to choose certain values for my geometry for this tutorial. However, make sure you're following far field boundaries that I discussed in my previous tutorial. Make sure that you're doing far enough away in all cases so that that your simulation is accurate. If you run the simulation and want to expand the geometry a little bit in all the directions, and if your answer changes, that means you haven't really satisfied the far field boundary conditions. So, but what I'm going to do is if you click on this point, right, and holding Control, click on this point, and then right click, you can apply a distance dimension. And so that distance that I'm going to make is roughly 2 meters, which is roughly 20 S over D, where S is the distance from the wall to the cylinder or sphere. And we can hit Enter and OK. You notice that it'll move it all the way over here. By clicking it, by scrolling out, by using your middle mouse, you can then click and drag this so that it actually covers the entire thing. We're going to add those dimensions anyways. So for instance, this dimension right here, if you click on that line, right click, apply length dimension. I'm going to make this roughly 15 meters. Click OK. Additionally, I'm going to make the distance from this corner to here 15 meters. So if I click that point, hold Control, click the other point, then right click, you can apply a distance dimension of 15 meters and click OK. Alright, so that's the sketch that we have. Alright, so that's the sketch that we have so far, but if you scroll in here, you'll see that this line right here, across from here to here, we don't want that because it's not part of the geometry. So essentially what you can do is you can click on this line here, holding Control, click on the semicircle, and then right click and split for trim. So what this does when you do that is the first one you click on, line you click on, is going to be what is split, and then the second one you click on is the tool for splitting. So now you can see that this has been split into 3 different parts according to this tool, and so we don't need this part anymore, and we can just delete it. Alright, so that's the sketch. If you click this button right here to reset the view, you can see it in the sketching pane, and so you can click OK. So again, STAR-CCM works by using 3D geometry. So the first thing we have to want to do is create a small extrusion. So if you right click on sketch 1 and then extrude, a new pane will pop up right here. We don't really care how much it is, it's just a small distance. So we can just keep the defaults for that and click OK. And you'll note that it's now extruded. It has a small thin thickness to it and still has the cylinder. So from this point on, we can close the 3D CAD. And when you expand the 3D CAD models, you can then see that there is a body 1 here. So what we want to do is we want to make this a part. So if you right click on it, you can create a new geometric part. These are some just options that you can play around with. Right now we're just going to keep all the defaults. After the part's been created, if you take a look at it by expanding the parts, you will see that all the surfaces there's only one surface. So what we're going to do is we're going to take a look at that by clicking on this button up here and seeing this is open scenes, and you can take a look at the geometry. And so this right here, if you click on the surface, you will see that all the surfaces are considered just one giant surface. So we don't want that. We want them split up so that we can label our boundary conditions. So if you right click on it and you split by angle, you're essentially splitting the surface by an angle of 89 degrees. So anything less than 89 degrees will be kept, and anything more than 89 degrees will not be kept. So we're going to try and change this to 45 and click OK. And now if you see, there are a bunch of different surfaces that you can use and access. So if you scroll out, we're going to rename these. So if you right click on them and click down here at rename, you can rename them. So this one right here, we're going to call the inlet. So if right click, rename inlet, and press enter. So this one right here, we can right click and rename this as essentially, we're going to call this axis or symmetry 1 because there's going to be one right here and one right here, and it's going to be either an axis or symmetry boundary condition. So we'll call this a axis, we'll call it axis symmetry 1. And this one right here, if you see right there, it's the one on top. This one we're actually not going to use, but we'll call this the top body. So we rename as the top body. Because I mentioned before, it only uses things in the z=0 plane. This has no points in the z=0 plane, so it's going to be completely ignored when we convert to 2D. This is in the z=0 plane, so when we right click and rename this, we're just going to call this body, because this is what we actually end up going to be using. This body 1 on, if you can see, it selects the cylinder, so we're going to rename this as the surface wall, because it's either the cylinder or the sphere. Likewise, up here, this is actually the top, if you can see. So so it's the top, so we'll call that the top wall. This is the second axis or symmetry condition. So we'll call it axis symmetry 2. And this is the outlet, so we'll rename this as outlet. Alright, so now that we've done that, the next thing we're going to want to do is create a badge for 2D meshing. So if you right click on body 1 and create a mesh operation, mesh, badge for 2D meshing, you want to select, body 1 is automatically selected, so you can also execute the operation upon creation. We're not going to do that, but if you wanted to skip a step, you could do that. So you can click OK, and you'll see down here in the operations, there's a badge for 2D meshing, a little explanation point next to it, which means it hasn't been executed most recently. So if you right click on it and execute, it has now created a badge for 2D meshing. And you can see along the sides here, there's little symbols next to our boundary conditions and our body. So this red surface symbol essentially means that that is what the body is. That's the surface in which there's going to be meshing. And then there's boundary conditions indicated by these red outlines. And this gray indicates that it's not used, which is what we discussed previously. Alright, so next thing you're going to want to do is right click and create a mesh operation. Mesh, you want to create an automated mesh for 2D, so you can select that option. So it asks you what kind of selecting meshers you want to use. We're going to use a polygonal mesher, but we're also going to add an optional prism layer mesher. That way we get a good resolution around the cylinder. for future for the boundary layer. So we can click OK. All right, so before we execute that and before we adjust some of the options of it, if you right click on body 1 again and assign parts to the regions, this way it knows what to mesh. We want to create a boundary for each part surface. So adjust this middle one here because we already broke it up into different part surfaces and we want each one of these to be a different boundary so we can set them to different boundary conditions. So you want to hit apply only once. This won't close without doing anything. You have to hit close, but if you hit this more than once, you're actually going to create more than one region. So don't do that. So you can click close. And you see down here, there is a region created. If there might be a region 2, that essentially means that you clicked apply twice. If that's the case, you would right click on it and delete it. Please don't have more than one region. In this instance, of course. So the next thing we're going to want to do is apply the mesh. So if we expand these options, we're going to expand the default controls. So the base size essentially represents the size that everything else scales on. I'll show you, for instance, the surface, target surface size, for instance. If you expand that, is 100% of the base. That means on each surface, unless otherwise specified through a custom control, the base is, the size of the cell is going to try and be 100% of the base, which is 1 meter. Now you can adjust this percentage of the base, or you can make the base size smaller. What we're going to do is we're going to keep the base size the same, but we're just going to adjust everything based on relative sizes, as well as the fact that if you actually wanted to change it so that it was an absolute value, you could click on the target surface size and change that to absolute. We're going to do that for a custom control because we're going to want a lot of cells around the surface. So what we're going to do is we're going to change some of these though. So because we want it growing slowly, we're going to change the surface growth rate to 1.05. Make sure you hit enter. See, if I click somewhere else, sometimes it will and sometimes it won't accept it. So like number of prism layers 10, if I go down to prism layer stretching, then go up to the number of prism layers, you'll see that it actually reverted back to 2. So hit enter 10 and hit enter. Additionally, for this prism layer stretching, so it stretches out a lot less, we're going to change that to 1.2. Again, hit enter. For the prism layer total thickness, instead of having the prism layers extend out really, really far, we're going to concentrate them near the cell. And so the base size, instead of them going 33% of the base size, which is 1 meter, we're going to take that a lot smaller and actually going to have it 1.5% of the base size. And so we can enter to that. Additionally, we're going to add some custom controls because the prism layers only have to be around this surface wall. If it doesn't have to be on these axes, the inlet, the outlet, or the wall at the top. So what we're going to do is we're going to disable those. So if you right click on custom controls, select new surface control, and open that up, you will see that you can apply this to any part surfaces that you want. So if you click this button to select those, expand the tree, and we want to apply this to any that's not the surface, any boundary condition that's not the surface wall. You can click OK. Expand the tree and see the controls. You can click down on the prism layers and change this prism layers to parent, which is all the default controls, and we can just disable it. Likewise, we can add a surface control to essentially concentrate a bunch of small cells around the cylinder. So if we right click on custom controls again, surface control, click on surface control again, and select the part surface of just the surface wall that we want, and click OK. You will see that we can click and expand down, and we can change the target surface size, not as the parent, but a custom value, which will allow you to edit this tree down here. And we wanted a target surface size. We're actually going to make it an absolute value of 0.002. So every cell is roughly 0.002 meters along that. So after we hit enter, now what we can do is we can execute this mesh. Before I do so though, I'm going to save my project. So if you save it, you can go to File, Save As. It's a good idea to do this often. I probably should have done it earlier. I'm going to just name this Tutorial 3. It doesn't really matter what you name it or where you save it. I'm going to just save that. And so now I'm going to execute the mesh. Alright, now that the mesh has been done executed, it hasn't really changed anything. So in order to see what the mesh looks like, if you open a scene and create a scene of a mesh, you can see that this is what it looks like. You can see that we have a whole bunch of cells concentrated around the cylinder. So with it expanding relatively high. So this is, you can also see that we have prism layers. These are what we specified, transitioning into the polygonal meshing. So we're going to call this a good mesh for right now. You could always adjust it if need be by adjusting some of these things and then re-executing the mesh. So we're going to call that mesh good. So the next thing we're going to want to do is select the physics. So by going to Continua, Physics, right click, and you can select the models. We want a steady thing. You will notice that it auto selects the recommended models, and then it automatically selected two-dimensional because it was a two-dimensional mesh. But if you want to make it axisymmetric, you actually will have to deselect two-dimensional and select axisymmetric to get some of the options. But we will cover that later on. So we're going to make the material a liquid. We're going to click segregated flow. It's just a constant density liquid with a laminar, that's laminar flow. So that's everything. So we can close out. So if you expand this model tree, you can see that this liquid, essentially, it automatically assumes it's water. But if you expand these material properties, you can change these values to whatever you want them to be. So I'm going to actually change them to 1,000 kilograms meters per cubed, and then the dynamic viscosity, I'm going to make it pretty viscous and actually going to make it 0.1. You obviously can choose these values. I'm shooting for a Reynolds number of around 6,000, so I'm treating my values appropriately. Alright, so that's all you can do for there. You can initially start out, so since the majority of the flow is going to be at roughly 6 meters per second to start, if you go to the initial conditions, click on velocity and click on the button next to value, you can actually change this to 6 meters per second in the X direction. And that's just an initial condition that it starts at. So we also are going to apply our boundary conditions. So if you expand region and boundaries, you will see all these options for the boundary conditions. So for the axis of symmetry, it initially says it's a wall down here. We're going to change it to a symmetry plane. Same with the other one. The inlet still thinks it's a wall, so you can change it to a velocity inlet. And the velocity inlet, if you expand these options, has a velocity magnitude of 6 meters per second. You can, of course, change these if you want to change the direction or the velocity frame, but we're going to keep those all standard. It's just normal automatically, normal to this plane. So we're also going to change the outlet from a wall to a pressure outlet. The surface wall is a wall as we expect, but if you expand these options, what we're going to do is we're going to set the shear stress to to slip, the way that there's no friction up here at the surface and nothing altering the flow from up there. Additionally, sorry, that is that's the surface wall. We want to be no slip. However, the top wall is what we don't want. We want to be slip. So again, sorry about that, but the surface wall we want slip, and the top wall we want to be in the slip conditions. So now that we've defined all those criteria, we're going to look at some of the solvers. These you can change if need be. For the velocity, you can change some under relaxation factors. The smaller this is, the longer it'll take it to converge, but the more stable the convergence will be. Same with the pressure. So you can change these values if you want by clicking here, but I'm not going to do that right now. For the stopping criteria, for the maximum steps, we want this to go until it's converged. So we're going to make the maximum steps pretty high and instead add the criteria of when the residuals reach really, really small values. So if we right click on this and create a new criterion from a monitor, and we can say, well, we want the continuity criterion to reach a minimum limit, this option pops up, of 1 to the times 10 to the negative 8th. And we can do the same thing for the x and y momentum limits. And again, you would actually want to take these as small as possible. I'm just arbitrarily choosing these values, but when you run this, you're going to want to make sure that your answer isn't changing even if you ran them to 10 to the negative 8th or 9th or 10th. If it's not changing as you transition to smaller and smaller residuals, that's when you know that your answer is acceptable. Additionally, on here, you can see that the logical rule here is OR. All of the ones you just created, you want to change to AND. So essentially, it says that it has to meet all of these criteria, not just one of them. So if the X momentum criterion reaches a really, really small residual, but the other ones are really high, it won't say that it's automatically converged. So now that we have that, what we can do is we can actually run the simulation. I'm going to save it first. And you can initialize the solution by clicking this button. And then you can run through by clicking this button. And you'll see the plot of residuals pops up, and you'll see that the residuals start going down. So we're going to let this run to completion. Alright, so now we can see it was pretty unsteady at first. I probably should have a slightly better mesh, and probably should have maybe some smaller under relaxation factors. However, it did eventually reach convergence. You'll note this says the stopping criteria for the continuity, X momentum, and Y momentum were satisfied. If you didn't change those to AND, it would say one of them, or two of them if you didn't change them all to AND. So what we're going to do now is analyze this data. So there's numerous ways to do it. Easiest way is to create a bunch of scenes of what you want to see. So if you right click on here, create a new scene, a scalar. So this would be like velocity, magnitude, or pressure. So if you click on create a scalar scene, down here, expand this, you can expand displayers, scalar 1, the scalar field you want to change. You can select the function. We're going to make it, actually let's make it just absolute pressure. And we can click OK. And you can see where there's some pressure differences. As you can see, it reaches really, really high pressure. If you wanted to change it so that it wasn't so square-ish, you could change by clicking up here on the scale. The contour style is automatic. If you change it to smooth filled, it's going to look more like that. Additionally, so you can right click on the scalar scene and rename it as pressure. You can create another scalar scene by right clicking and creating another scalar scene. This one we're going to do the same thing on, only this time for the displayers we're going to make this absolute velocity. So velocity magnitude. We can select that and click OK. You can see that definitely have a wake region down here and a stagnation point up here. And again, this is all not smooth, and so you can change them by clicking on the scalar field, changing it from automatic to smooth filled. Alright, so additionally, what you can do is you can add some vector fields if you want. So instead of a scalar field, you can then get vector plots by, again, right-clicking on scene, new scene, vector. If you zoom in, you'll see that it chooses a pretty large thing. This is pretty unintelligible. But if you click on vector scenes, similar to before, if you go to displayers, explain vector, you can change the vector field. It's already set to velocity, so we're not going to have to worry about that. Additionally, if you select glyph, you can change essentially the vector scale. I prefer it to be screen size, so it looks more like this. You can see how everything goes around. You can zoom in along the plots. Additionally, you can change it to part size, which isn't very good. You can also change absolute, which is still pretty decent. Additionally, if you wanted to expand this, you can change the absolute length manually. So if you want to make this 0.05, for instance, you can then see a better picture of what it looks like. So you can change this to whatever you want it to be. That's still maybe not small enough. So you can get a good picture of it in that manner. You can also change the, by clicking on here, you can change the tip scale. So if it's too big for you, you can make it smaller. So it's easier to see. So that's what we can do for that. So after we do that, of course, what we can do is add some streamlines. The first thing we're going to do for some streamlines is just create a new simple geometry scene so that it looks relatively normal. Again, if you click this button, it'll reset the view. So if you go all the way up to derived parts, let's minimize some of these just so I can find it. Derived parts, right click on it, new part, streamline. So what we want is want a seed part, which is essentially where it starts the streamlines. We're going to set that as the inlet. Click OK. We're going to change this resolution to really, really high. You probably could make it even higher than I'm choosing. It'll take some time, but this will do a better job of seeing the streamlines near the surface of the surface wall. So if you zoom in after this, you can see how it bounces up. So if you added more, obviously you could see better streamlines. So this is just zooming in. So then we can close out of that. And so now we want to say, well, what happens if we wanted to do this for, this is all for a cylinder, right? So what happens if we wanted to do this for a sphere? So what we would do, the first thing you would have to do is you want to clear your current solution. You're not going to be able to get this back, so I would save it. And I would save it as something else. That way you can go back and look at it in case you want to change some of the essentially scenes or some information about it. So save it as something else first, obviously. And then you can just clear the solution. And when you clear the fields, this is going to keep the same mesh. So by keeping the same mesh, we can model the same thing easily. But the only difference is when you go to Continua, for the physics, when you right click and select models, you don't want it to be two-dimensional. What you want it to be is axisymmetric. So if you select that option and then close out, now when you go to the regions and go to the boundaries, these axis or symmetries planes will now have an option way at the top to be called an axis, and that's what we're going to change them to. And then once we have that, we can reinitialize the flow. and we can run the simulation from then on out. So I recommend, as you notice, it took a while to do that for Streamlines. If you do that, with running Streamlines, it's going to run that for each iteration. So instead of doing that, what I would do is I would stop it. It's going to continue moving. And so what you want to do is actually the geometry stream with the Streamlines in it. If you open it up, there's a Streamline stream. You want to just delete that. Otherwise, it's going to try and calculate the streamlines for each iteration, which does not really concern you. So then from there, you can actually just run it. And if you look at the residuals, it's going to be doing the same thing. All right, so you would run this to completion. I'm not going to run it to completion because all you would have to do is reanalyze everything. All the scenes should update, but if they don't, you can right-click on them and refresh as an option. And from there, you could analyze and compare both the cylinder and the sphere with the same mesh. So if you have any questions, feel free to let me know in the comments, or of course, contact your instructor or whoever gave you the problem at hand. Thank you very much, and have a good day.